Okay, thank you. Let's get
混合倡议。美国呢曾经呢是率先这个甲醇的燃料混合，加州啊是把17000个这个甲醇的这个车辆呢是放到了这个街道上，但是呢在90年代呢却退出了舞台，因为当时呢这个石油呢非常的便宜。那么现在中国呢，又是处于世界前沿，是在这个甲醇的这个混合的研究方面有很大的进步。那么今天呢，我们会听到这个讲者啊，会涉及到了我们这个全球的甲醇燃料混合。那么在讲到美国呢，我们的这个目前呢，美国的能源信息局呢，也是关于中国的这个甲醇的燃料使用呢，也是进行了研究。那么我们再来讲一讲我们的介绍一下我们的讲者，然后呢，再让他们一一来进行演讲。
Is Mr. Jin Zhang Yang. He's a senior chief engineer of Shanghai Hapu Auto Corporation of the Geely Holding Group. Mr. Jin joined Geely in 2003 and began R&D on Geely's methanol car in 2005. He now leads all R&D piloting of Geely's methanol vehicles. Geely is one of the most popular auto manufacturers in China, with a sales volume of 760,000 vehicles in 2016. Geely is also a Fortune Global 500 company, and the Geely Holding Group also owns Volvo Cars and the famous London Black Taxi Company. Our next presenter will be Gil Danker from Door Chemical. He is an Israeli industrialist and businessman. He serves as president and chairman of the board of the Door Group. The Door Group is a leading advocate for implementing the use of methanol in fuel alternative in industry and in transport. Door Group's companies are Door Chemicals, Door Ecology, Carmel Chemicals, and the Verilit Elex. Mr. Danker holds a bachelor degree in mathematics and physics from, I believe it's the University of California, Santa Cruz. Our next presenter will be Peter Gross. Peter is an operation analyst at the U.S. Energy Information Administration, where he leads the natural gas market teams doing analysis of modeling in natural gas energy markets. During his 10-year tenure at EIA, he has also worked in industrial and biofuels energy consumption data analysis and forecasting. Peter holds a PhD in chemistry from Princeton and an MS in statistics from Brock University. Next will be Harold Sun from FETEC, one of the member companies, the Methanol Institute. Harold Sun is currently technical director at FETEC, responsible for new technology development. FETEC is a Chinese-based company that is at the forefront of methanol fuel blending technology. Harold received his BS in 1982, MS in 1987, PhD in 1993. For over 20 years, he's worked on the performance and emission development of generations of diesel engines, large and small, on U.S. emission standards as U.S. emission standards evolved. He has authored or co-authored over 40 technical publications and received 26 patents on the topics of diesel engine combustion, engine system integration, control, turbocharging technologies, and aftertreatment. And then our final speaker in this panel will be Vikram Rao. Vic is Executive Director of Research Triangle Energy Consortium, a nonprofit in energy founded by Duke University, North Carolina State University, RIT International, and the University of North Carolina at Chapel Hill. Its mission is to illuminate national energy priorities and those of the world by extension and to catalyze research and address these priorities. Dr. Rao is author of a book, Shale Gas, The Promise and Peril, and co-author of the book Sustainable Shale Oil and Gas, Analytical Chemistry, Geochemistry, and Biochemistry Methods. And with that, we'll have our first presenter. Again, this presentation will be given in Mandarin, so you will need to put your headsets on and click them on. Mr. Jin.
大家好，我是来自中国的吉利，我叫金新阳。今天呢，是由我来介绍给的吉利的甲醇汽车的研究。下面呢，从这几个方面介绍。第一个是介绍一下我们的企业。 这个我们吉利的企业呢，现在有3个大板块，第一个是吉利汽车集团，第二个是沃尔沃的汽车集团，第三个是吉利新能源商用车集团。这个吉利在汽车榜上全球也是最具有价值的品牌。
In 2017, we are awarded one of the most valuable brands, and we are the only Chinese auto brand on this global Fortune 500. And this PowerPoint shows the global plant layout. Geely Auto has 12 vehicle manufacturing plants and 6 powertrain plants in China and 6 CKD and SKD factories abroad. In terms of R&D, Geely has invested greatly. And we have 4 design studios, one in Shanghai, one in Gothenburg in Sweden, and one in Barcelona, one in California. In terms of R&D, we have about 6,000 science and technology-focused personnel. So design studio, we have over 500 designers, and we have more than 2,000 research personnel in Europe. So this is a picture of our newly established testing R&D center, which came online in the second half of 2016. And let's look at the new energy strategy. So we aim to have 90% of Geely Auto sales will consist of new energy vehicle sales by 20%. Geely will push forward with research into hydrogen fuel cells and metal fuel and fuel cells. And Geely will become market leader in new energy, lightweight material technologies, and intelligent and connected systems. Now I'd like to talk about our R&D review. So first of all, let's look at our R&D review. Actually, in 2005, Geely started research in alternative fuels, and we've worked 12 years. We've invested over 1 billion RMB, and we've also broke through several key technologies. We've also established 14 methanol auto models, and we've also passed the verification of the Chinese authorities. Let's look at our R&D history. So over the past 12 years, we've gone through 4 stages. First is 2005 to 2010 technology preparation. Second stage is 2010 to 2014, it's product R&D. Third phase is 2013 to 2016, product upgrade. And starting from 2016, we're going to work on future technology improvement. So in terms of technology preparation, especially in 2005 to 2010, we started co-starting, fuel supply, flexible control, and alcohol resistance issues. They are successfully solved. And also, we've successfully launched our first generation methanol powertrain and methyl car. We've also achieved over 40 key technology patents. So the picture on the top was taken in 2006. It was the first generation car. So this car today is still in good conditions. The pictures in the middle, on the left is test in harsh environment, high temperature. It was taken in Xinjiang province. It was 48 to 50 Celsius degrees. The picture in the middle is tested in high altitude. It was tested in Kunlun Mountains. The picture to the right is tested in low temperature. It was tested in Heilongjiang province. So from these pictures, we can see that our methanol vehicles are tested in very harsh environment. So let's look at the bottom pictures. We were doing reliable tests on our methanol methanol test, and in order to pass this test, normally the standard is to go over 30,000 miles. However, our cars have gone through 80,000 miles. The last is So let's look at our second generation vehicles. This is second generation methanol car, the first certified methanol vehicle and a model in MIIT's pilots. And we've also upgraded of our methanol powertrain. Our second generation, we've also done pilot test authorized by MIIT. So from all these pictures, we can see our first 150 methanol cars in Jinzhong in Jiangxi province. So all these pictures are showing our pilot cars. The third stage is our product upgrade. So we integrate our resources. We've also commercialized our production. So under Geely's management in Hunan province, in Ningbo and Linhai, in our bases, we've upgraded our capability of mass production of methanol cars. We have newly built methanol car base in Jingzhou and Guiyang. In addition, we've also developed our fourth generation of new Dihao methanol finished piloting in Iceland. At the same time, in our pilot, in order to win more customers and meet more demands in 2016, we also developed more models of vehicles developed in 2016. So the two models are also displayed on this PowerPoint.
And now we are talking about our technology improvement. Here now we are doing research to use the physical property of methanol to make it more friendly to environment, and we are going to launch next year. And next one is exploring the turbocharging and direct injection technologies. And also we are working on our fifth generation methanol car, and we also developed DUPE international cooperation to promote green methanol applications. And now we are going to the methanol automobile products. Here we show on the top of the slide on the right, this is our first generation car. And following by our second, third, and fourth generation. So you can see we have all different models to satisfy our customers. And here is our trial running. We have been running over 1,000 cars in five provinces, and it has been over 400 kilometers and total mileage over 200 million mileage. And there is no alcohol-related failure or accident in the pilot, prove the performance of this car. And here in the map, showing where we are running these cars. And the piloting result proving the power, fuel economy, and everything of this methanol cars. And our national and local governments, industry, and all the related parties highly recommend this car. And in 2017, we are going to promote this vehicle in different provinces. Also, in foreign countries like Iceland, we have it running in 2015 in Iceland. And now it has been more than 1 year, and it's still doing very good. And the society there and their and the organization there also highly recommend our car. now we are talking about the technology level. Over 10 years research and practice, we have breakthrough some key technologies and get over 100 patents to accumulate our experiences. And we have 4 different kind of methanol engines and over 14 different methanol vehicles. And we also undertake the country's technology projects. And here it's in May 2015. It's the recent 3 years that we are inspection our pilot testing, and our experts highly recommend the result and improve the quality and improve it in the leading level internationally. Now we are going to the industry chain. Under the Geely Group, we have Ningbo, Ningxia, and all the companies we can produce the car together. And also we have new plants in Shanxi and Guizhou to focus on methanol cars. This is the plan of one of our plants to show how it works there. And this is the pressing plant in our plant. And this is also in Shanxi. In Shanxi, it's in the welding plant there, and it can take over 90% of work. And this is the painting plant. And this is our assembly plant. And we have full preparation for producing methanol cars and also forming component supply chains. So the conclusion is that we have variety of source, and the source is from coal. So we also use it in clean way. We don't just use it. We don't use it in the way to create the pollution and particles. And second, we use sulfur coal, ash coal, and all these different materials to increase the production quality. And here we also use biomass to get it for its safety, cleanness, and renewable. And in Iceland, we also, by capturing plenty of industrial emission of the CO2, so in this plant we can produce over 200,000 tons of methanol for the methanol cars. And the third conclusion is for our technical merit. We have over 12 years research, and we filed over 100 patents, and we are world leading standard. And for our marketing verification, we prove the safety and environmental friendly performance. And the third is our vehicle detection. So we have passed multiple regions for the tests. So we also meet the Euro 4 standard. And the Euro 4 standard is like 80,000 kilogram standard, and we meet it. And for the emission detection, we also match all the standards, especially for the methanol emission. And for 2 years, we are sure that the emission is 1.4 milligram and it's lower than our national standard, and also lower than the U.S. level 2 standard. And the fifth one is for our industrial chain. We have 14 different car models in 5 different production bases, and the 6th is our next plan. We are going to use the alternative fuel in China soon. So, and for next is our future. That we know that using methanol is the trend in the whole world, and we can never stop developing this new technology. We need to develop the methanol economy to improve the greenhouse effect. Now our technology is very mature, so we believe methanol alternative will be developed rapidly in China, and we hope to put together all the effort from our global partners to improve our environment worldwide. Thank you.
Asked us to be focused, so I'll talk about food. Up to 50 years ago, not all of the people around the world had proper food. This has changed. But what has happened since then is that not all of us have proper air to breathe. And pollution from cars is one of the major reasons why we don't have good air to breathe. As a matter of fact, in the United States, more people die because of pollution due to automobiles than car accidents. It's estimated to be twice as much. So I will try to focus on the environmental aspect and how methanol can serve how methanol can assist in improving the situation. Now, taking into consideration that there are 1.2 billion cars now, and the growth rate is 100 million cars a year, we are really facing, in a matter of 15, 20 years, a catastrophe. And mind you that the diesel and the gasoline are going to remain the major means of energy for the automobile industry, unless we do something about it. So I'll show you a short film about what we are doing as far as using methanol in fuel, and then we'll go into some details.
Imagine a world where rapid economic growth is environmentally friendly, where the air is clean and the environment is protected for future generations. A world where clean, renewable energy is inexpensive, safe, and effective. A world where society is both willing and able to afford the cost of a clean environment. A world where the energy for light, heat, transportation, and to power industrial plants is derived from renewable resources. Today, the increased sales of petroleum-fueled vehicles is a key factor in a crisis of global proportions. Door is at the forefront of worldwide efforts to find greener, non-fossil energy sources. Door is world-renowned for breakthroughs in energy for transportation, industry, and electricity. Door's prime initiative is the utilization of methanol for transportation. Methanol is a renewable energy source that can be produced from a wide array of feedstocks, including natural gas, biomass, hydrogen, and CO2. Most importantly, methanol is a fuel alternative that is a cleaner, safer, more cost-effective, and competitive energy source, providing consumers with true freedom of choice. Thanks to Door's advances, fuel mixtures consisting of up to 15% methanol can be used in a standard automobile engine with virtually no changes. Door collaborated with the Department of Energy, the Environmental Protection Agency, and the Prime Minister's Fuel Choices Initiative program to bring together a groundbreaking M15 standard. This has led to international collaborations such as with Fiat Chrysler on further development and implementation of methanol in their fleets of vehicles. Flexible fuel vehicles are currently able to use concentrations of up to 85% methanol. Door is currently pursuing a 100% methanol solution for diesel-fueled heavy-duty vehicles. Methanol offers energy security by allowing maximum diversification of energy flow tracks from a wide variety of sources. Methanol provides a choice, a true environmentally friendly alternative to existing fuels. Door is leading the energy revolution with smarter, cleaner, more accessible, and simpler alternatives. Door, illuminating the way for a better, greener future.
So basically what we want is to create an environment in which methanol will be part of the energy basket, in particular for transportation. It makes sense, and yet it hasn't happened so far. So the economics is straightforward. Calorically adjusted, the price of methanol as compared to diesel and gasoline is cheaper. On an average, you can see it there. So from that point of view, we are in business. It's cheaper. On the average, 15 to 20% cheaper. This is the program of the Israeli Prime Minister's office, where the challenge is to replace 60% of the oil-based fuels in Israel. You can see methanol, CNG, electric mobility, and biofuels. I can't guarantee that it will all happen, but as far as methanol, we are on track and it's happening. By the way, the idea of the Israeli Prime Minister's office is not only to have methanol or alternative fuels in Israel. The idea is that it should be across the board, and that's for energy security considerations. This is the outline of the Israeli M15 standard. It's the first time that Israel has created a fuel standard. So far it was Israel has used the European fuel standard, and it was created in a manner that can be adopted by the European community. All the trials we've done were done along with GRC, which is the agency at the European community which looks after the technical aspects of any fuel when they have a new fuel. So why should it be there? It's lower priced. The emissions, and I'll show you figures, are better. It's safer. The methanol burns in a lower temperature. As a matter of fact, it's used by racing cars because of safety. It does have energy efficiency. What we see is that even with M15, you get more mileage per calories. And it can be used by any car, by existing technology, and you can utilize existing infrastructure. This is a critical issue because all other alternatives, whether it's electricity, hydrogen, CNG, you have to create new infrastructure. Using methanol, you can use the existing infrastructure. And obviously, using natural gas, which is available throughout the world, you create new economical opportunities. So this demonstrates the issue of safety, and safety is a critical issue when we want to introduce a new product to such a regulated industry, and rightly so, because at the end of the day, it has to be safe. Methanol is safe. We have, throughout the years, we've done work as far as methanol in transportation, power plants, and steam boilers. And from doing one, we've learned for the other. Our power plant technology is already commercial, and if I have time, I'll show you about it later. So let's start with the M3. M3, as far as the European standard, it's acceptable, it can be used, yet it hasn't happened. Since we have launched the M15 standard, the industry is more open to accept M3. So there is an issue of, there is a lot of hesitation, there is a lot of fear, and this is one of the issues we have to address, how to overcome it. But the fact is that from the point of view of the automakers, and they are a key player in this challenge, and the success is that 3% methanol in the gasoline blend can be used without risking your liability on your car. M15. The fact that we've had Fiat Chrysler, FCA, as a partner is a critical issue. In my view, one of our challenges is to get the automobile industry to be partners in our efforts. And they have good reasons to do it. Fiat was the first automaker to accept and to announce. They have announced in November 16 that they accept methanol as a legitimate fuel. And they've done it while the Automaker Association still is not accepting methanol. We started with this Fiat 500 because Fiat sells 500,000 units of Fiat 500 annually. It's 0.5% of the total number of cars sold. And the changes that had to be done for Fiat to guarantee Fiat 500 as an M15 fuel were minimal. It was a matter of few dollars changes. Now, these are the emission results using M15, and actually the most critical, the most interesting figure is the one where we see the lowest reduction, and that's CO2. We see that CO2 reduction is 1.5%. Yet, from the automobile industry, it's a huge figure. In Europe, the automobile industry is being fined for CO2 emissions above a certain level, and the fines are in hundreds of millions of euros. Here, the 1.5% amounts to 10% of the overall quantity that they have to reduce. And for Fiat to get a reduction of 10% without any investment, it has a huge value. And this is the reason why Fiat is joining and accepting M15. And as I said, we have to get the other automakers to participate because we need to have a situation where all automakers accept methanol. This is a key issue to succeed. I know that some other automakers are looking at it. Geely is here. Volkswagen is doing so, but we have to motivate them to talk to us, to participate with our challenges. This is a standard car. Don't tell your president, Mr. Trump, it was produced in Mexico, but it's running on M70. We've done nothing about it. It's a great car. It's made in Mexico. And for the past 4 years, we have a fleet of those cars. They are running on 70% methanol. We had to do nothing in order to have them run so well. Here, what we can see are filters with comparing the filters of regular fuel 95 RON, E10, and M56. And you can see how clean the methanol filters are. Okay, so I'll skip few slides. The M100 is a huge challenge, and it's an interesting challenge. I'll talk for a few minutes about gas turbines for electricity production, but to sum up the issue of using methanol, we have to do it carefully, we have to do it right. There are reasons why methanol was not accepted. Methanol behaves differently than ordinary fuels, so we have to be careful. We shouldn't do mistakes because the reputation will be terrible. But if we'll do it properly, it's a fantastic addition to the fuel basket, which in any case, with the growth rate of automobiles, the automakers will have to find an additional means of energy. Fuel will not be sufficient. Gasoline and diesel will not be sufficient to run 3 billion cars. So I'll sum up because the conversion of a gas turbine into 100% methanol from a technological point of view was much more challenging than to convert a car. Converting a car is not very challenging as compared to a gas turbine. We've done it because of environmental issues. This is a Pratt & Whitney gas turbine. What you can see is the reduction of emissions. It's dramatic. The emissions are, it's much cleaner, and that's where we are going towards. Thank you very much.
So I'm Peter Gross. I'm from the U.S. Energy Information Administration. And part of our work, or most of our work, is collecting and analyzing energy data of all sorts. And we do it both nationally and internationally. And I was asked to come here because we recently did a study, or commissioned a study, as Greg said, for China methanol consumption. And the reason we did this was because we had a little bit of a issue in terms of reconciling supply and demand. And we get our supply data from various sources, we get our demand data from various sources, and we have to reconcile that, of course, at the end of the day. And we're finding, at least in terms of our liquids fuel demand, we were having some issues. We commissioned this study to help us with those issues, in particular because we thought methanol was the so-called culprit. And this study was also valuable because it gave us insight into how methanol is used as a fuel, in particular, not just for blending, but also in terms of its derivatives, which I'll talk about in a moment. Just a quick overview. I know time is short and I may have to buzz through some of these, but when we think about methanol at EIA, we have to think about it in the broader energy picture. So We have to think about China in terms of its changing energy mix and its economic growth, which impacts methanol consumption directly because of its purposes to do with chemicals, especially. We also, as relates to this particular Argus study that we commissioned, we have to think about methanol use for fuel, both, as I mentioned, for direct blending and as derivatives. We also have to think, because when we think about our energy projections, we also think about the environment and greenhouse gas emissions. So we have to think about the feedstocks. As was mentioned in the previous panel by Simon Zhang, China continues to use coal and coal resources for most of its methanol production, and that has an impact on greenhouse gas emissions. We also, as I'll show you in a minute, think about projections with respect to methanol and other energy sources, and I'll show a little bit of how the Argus data that we commissioned played into all of our analyses. Kind of a wordy slide, but I'll run through it a little bit quickly. What Argus actually told us in this study: the methanol supply and demand have risen rather quickly in China. I'll show some pictures of that, especially in terms of the fuel use. Coal still accounts for the majority of the feedstock and will continue to do so, as I mentioned earlier. Some Chinese provincial governments, and this was mentioned by our first speaker, are working towards standardizing methanol blends, making them legal, even though probably some illegal blending is still being done in China and will continue to be done for a while. But it's an economically viable fuel in China. And refiners also are in this game. And as we learned from the study, if the methanol is blended outside the refinery gate, there's a tax benefit, or no tax, should I say, which is a tax benefit on the methanol. And not only that, but methanol, has been mentioned, also has value in terms of its octane. Oops. As I said, we reconciled the Argus information with our own data, but we also then use that to help with our projections. We present an international energy outlook every year from my agency. We are going to use, have not used yet, but are going to use this study and the data from it to inform our projections of fuel consumption in China, gasoline, how gasoline demand will impact methanol consumption, and vice versa. And we're also, and was mentioned earlier this morning, we're also thinking about bunker fuel usage. And I'm not so convinced that it's going to be very relevant, even in competition with LNG, but we are thinking about it in terms of our projections. So as I mentioned earlier, we have to think about the overall energy picture of China, and this gives a brief historical perspective of how quickly energy use has, it's no surprise, how energy use has grown in China, the bulk of it being coal. And of course, coal is the main feedstock for methanol, and so that will, even though coal is tempering and will continue to temper in our projections in use in China, it still is a major player and therefore a major impact on the environment. Extending that historical data out to our projections in the International Energy Outlook, this is from our last year's International Energy Outlook. Again, methanol has a big role to play. We see, again, no surprise, petroleum and other liquids continuing to rise, given that the Chinese are going to buy cars like everybody else, and they're going to use them to drive. Coal is tempering, but that's not because of any slowdown in methanol production. That's due to some gradual shifting away from primary steel production and, more importantly, away from coal-fired power generation towards natural gas and renewables. This is just a breakdown of the petroleum consumption in China. Again, just a historical snapshot showing that gasoline is an important player. Obviously, in China, will continue to grow. Diesel is still the major player because of all the freight that's transported and its use also in mining and agriculture and construction industries. LPG is also a growing liquid fuel in China, and that plays a role both in the chemical industry and in residential and commercial sectors. And I'll talk a little bit about a derivative that's used in LPG that's based on methanol. This is just a quick projection of from our IEO 2016, again, of just breakout of the transportation sector fuels. again, a lot of growth for gasoline available, which translates into growth for methanol use. I don't think anybody's talked about this yet, kind of giving a very global perspective on the methanol production scene in the world. And what continues to amaze me is how big China really is in this whole methanol world. By far the biggest consumer and producer, although we've noticed that of late, probably in the past year or so, its imports of methanol are continuing to go up, and that plays into a little bit of China's need and balancing of, having some chemical industry, some olefin plants, ethylene plants on the coast of China, and weighing whether or not it's more economically advantageous to import that methanol from the Middle East and now more and more the United States in the future, or whether to bring it in from more the central and western parts of the country where the methanol is actually made from coal. This is just showing, sorry. All right, so on to the real story that Argus informed us about, which was methanol and fuel. There's, of course, the direct blending that we've been talking about, and then there's the methanol derivatives, MTBE and dimethyl ether. The MTBE is blended into gasoline. MTBE is an oxygenate. It used to be used in this country. It went out of style in kind of a parallel track with the oncoming of ethanol use in this country, which replaced it as an oxygenate. It should be noted that it's not an environmentally friendly fuel or fuel derivative, and it's essentially, for all practical purposes, banned in this country, but yet it makes up a big component of the methanol derivatives used in China and elsewhere in the world. The DME, the dimethyl ether, is another methanol derivative used in LPG in China. This is a nice little breakdown of China's methanol consumption, again, as we got from the Argus report. You can see that the fuel itself, methanol used as fuel, has been increasing rapidly in China by fivefold over the past 10 years. And again, we see this trend continuing in the future. And I've broken it out here between the methanol in blue, actually blended into gasoline, versus the derivatives, MTBE, and a little bit of MTG, which is this methanol to gasoline process, which is actually quite minor, and as well as other uses, DME, which I, again, talked about within LPG, and some industrial direct burn. But again, a lot of growth here in the recent past and a lot of continued growth. And this is just kind of looking out and seeing historically where this fuel application of methanol actually fits into the overall methanol consumption within China. And it's been a substantial piece of the pie in terms of China's overall methanol consumption, with the chemicals taking up the rest of the pie, as it were. Even though, as you can see from this graph, the fuel applications represent more than a third, in terms of actual growth of methanol use, we foresee, and we were informed on this by the Argus study that we commissioned, that methanol growth is mostly going to be seen in the chemical industry in terms of making olefins and plastics and so on, not so much in the fuel industry. This goes back to harping again on this point of the feedstock issue. I've heard a lot of people, or not a lot, but some people talk about the greenness of methanol, shall we say, in the future, perhaps coming from renewable sources. But the biggest user of methanol right now is China. And again, as I've said, we don't think China is going to go real green with respect to methanol anytime soon. Coal will still be the primary feedstock. And as Simon Zhang mentioned earlier, coal is the dirtier side of methanol production. This is just a picture of MTBE consumption, again, re-emphasizing this idea that it's not just methanol blending, but it's methanol derivatives that are being used for fuel within the Chinese fuel picture, fuel demand. And even though this is kind of a lousy graph, you really can't see much here. It was mentioned by our first speaker, and I hope I pronounced this right, the Shaanxi province is probably the leader in terms of methanol blends, where I think M15 has actually been standardized and made legal. Around the country, you have other pilot programs experimenting with the use of methanol, and as I said, this is expected to continue. A couple of methanol plants in the United States that have actual Chinese investment. Again, the import of methanol, which is made from natural gas, unlike what the Chinese do, is going to become, we think, a growing part of the methanol supply, but again, nowhere near what the production is in China. And that's it. Thank you.
Good morning, everyone. We've been talking about methanol for many years. Now, I think it's a good time to look at it again, why we talk about the methanol and the potentials using the methanol for the automotive applications. In the past few decades, and on and off, we talk about the methanol for automotive application in 80s, early 80s. Ford launched limited mass production with methanol for the Escort and for the Taurus application, accumulate some useful information. It's those information available in the website, which was very encouraging. And however, those methanol application for the automotive has been faded due to the rapid drop in gasoline prices. And lately, in China, government has been pushing, encouraging the methanol application for the automotive, mainly due to the alternative energy, and especially for the regional areas. And also in the other parts of the world, we've been working with some other customers, India, Israel, and Malaysia, and Sweden, Finland, for methanol application used in the medium-duty trucks, passenger cars, and the piloted boat and marine applications, which were very encouraging. We get to some details later. So in the U.S., we're looking at the methanol as a potentially energy carrier to help the export of the natural gas. That's a big potential here. Sorry, not so sensitive. Yeah, no, got it. Yeah, thank you. Yeah, okay, thank you. We've been working with local OEMs in China, and over the past 10 years, looking at the M100, 100% methanol application for the passenger cars. And of course, to convince the customer it's a viable powertrain application, we bring the vehicles to the high altitude, tested high altitude compliance, and also the cold ambient, because the cold start for the methanol has been concern for many, many years for the many customers. So we need to collect a solid data to convince a customer it's a viable solution. So we collect some useful information. Here now we just highlight the methanol, why methanol is good alternative for the gasoline engine and also light-duty diesel engines. First of all, methanol is very clean. It's basically smokeless combustion. And methanol, it carries oxygen itself, so it's easier for the air handling system and reduce the air drop in the intake system. And also, we demonstrated methanol can pass methanol can pass EPA 2015 emission regulation in terms of the particulates. And even with just single three-way catalyst, it can handle those regulated emissions. And we have data to show you that the methanol is actually more efficient than gasoline engine. It's very close to the diesel application. And we're looking at the diesel in terms of particulates emissions. And the y-axis is the thermal efficiency. So it's very close to diesel in terms of thermal efficiency, but except that the soot emissions is very, very low. So in terms of the off-highway or on-highway, the both can easily meet the particulate emissions. So that's an encouraging part. We're looking at this a little bit more technical details, but for those people interested, it's very useful information. On the left, it's a gasoline engine thermal efficiency, brake thermal efficiency distribution along the operation range. We know that the automotive engine operating all over the place, light load, heavy load. So this x-axis is the speed, and the y-axis is the torque, right? So you can see that, let's say, the 32% thermal efficiency in these small areas. For the methanol, easily get a 33 or even better. And so the methanol is the more efficient than the gasoline engine. And with this, we just, without real fancy engineering optimization for the engine, just basically take the existing production engine and upgrade with the fuel system, and so easily get very encouraging results. And we also know that the fuel itself, the methanol, is a low carbon fuel, and plus that more efficient combustion. So in terms of greenhouse emissions, the CO2 emissions, again, the gasoline engine is not as good as the methanol engine. The methanol engine, for the same, let's say 850, the CO2 emissions, and cover the wide range as low CO2 emissions. So in terms of the greenhouse gas emissions, CO2, the methanol is much better than gasoline engine. Of course, this one does not include the process to create the methanol, right? There's a production methanol, greenhouse gas emissions is not included here. And aldehyde emissions has been concerned as well, and we know that in the past 30 years has been a subject of the regulations, especially for the, similar to the ethanol. Brazil has special emissions regulation for aldehyde, and that's the only one, to my knowledge, beside the US. And we took the effort to test it, and as Mr. Jim mentioned earlier, yeah, it's consistently low, and it's similar to the gasoline applications. And we understand the aldehyde is mainly created during the cold start process, and also with the lack of oxygen. And we tested, it's low, it's only 0.8 for this, the milligram per kilometer. And it's even lower than the US LEF3 emissions. And of course, I have to mention about details here is that this is tested at the NEDC cycle, and US LEF3 emissions regulated at the FTP cycle. But this one still shows very encouraging, and it's passed no problem with China 6 emissions. And also the durability of the methanol components of the fuel system has been concerned as well. We took the effort to test the emission level of the methanol-fueled engine over the lifetime of the vehicle. And, sorry. Oh. There we go.
The next slide?
Yeah.
Next slide, right?
Yeah. Sorry.
This one.
Yeah, somehow this line did not show up. I don't know why.
It's there. Yeah, it's there.
No, I'm trying to see the regulation, where the regulation is, but sorry, yeah, something missing in the convert the data. Yeah, it's supposed to be a line here. This is the regulation limit, and we're showing this emission regulation. This is supposed to be CO2, if I remember correctly. Sorry, CO. And it's fluctuated over time of 160,000 kilometers, but consistently below the emission limit. And the total hydrocarbon is, again, the point, supposed to be 0.1. This one consistently below the emission regulation for the China 5 emissions over the useful lifetime. And the NOx, of course, is low because a lower flame temperature of the methanol fuel. And it seems to be the three-way catalyst is very effective just dealing with the methanol as well, even without the optimization of the formula of the catalyst. So this data shows it's durable, reliable over the useful lifetime using the methanol. So we work with OEMs in China over the past 10 years, and we currently have more than 2,000 vehicles, methanol vehicles on the market. And now we're working with different suppliers on a pilot boat for the inland marine application, the off-highway engines, construction machineries, and also we're working with different customers, OEM customers for the methanol diesel or methanol natural gas dual fuel applications on the highway application. This particular, little picture showing that the pilot boat, we work with a Sweden customer. They have a video, it's entertaining, but it's not taken by professionals, just remind you. So, however, it's entertaining, showing the truth, conveyed how the customer was thinking about. Yeah, it's coming.
This is a historical day. First time ever this methanol pilot boat is operating on renewable fossil-free methanol. A day to remember will set the standard for shipping in the future.
I'm not sure you catch the voice in the background. Yeah, but basically it says first time ever application for the pilot boat with the methanol, and showing that's a future of the inland marine applications. And yeah, something that's not as good as I expected. They're supposed to be in the front of the videos, but anyway, that's. It's encouraging, yeah. So our message is methanol is cheaper and cleaner and reliable and is more efficient than the gasoline engine. It's supposed to be a future for address those emission, highly polluted areas that as an alternative. Thank you.
Anybody that follows me on Twitter would have seen a link to that video, so it's out there. Our final presenter, Ben.
Yeah, before I get into this thing, let me I won't exceed my time, okay? Take a minute or two to comment on a couple of things that just happened. So one, there was a comment made that despite the calorific deficit, methanol is cost effective. True, probably in some respect anyway. Then the last speaker spoke about higher efficiency. So I'm going to give my take on that, okay? My take on it, I did a back of the envelope calculation which says that if you have M15, you lose about 6% on calorific intensity. So that's less mileage if you just kept with the car. But methanol has higher octane rating, but more importantly, much more importantly, it has a higher heat of vaporization. So if you direct inject, not ported injection, not all cars. By the way, since about 1992, all cars went to injection of some sort, but somehow there was called ported injection. If you direct inject, which is what these people are doing, directly into the cylinder, and here's what happens. It evaporates and it cools the cylinder down. So the result of that is you can go to higher compression, because what higher compression does is produces frictional heat, which then causes you to bad things to happen. That's why you need higher octane fuel. But if you direct inject, then the latent heat of evaporation is going to give you the benefit that you can go to. So I did a back of an envelope. If you take a 9 compression ratio engine, which is pretty normal, go to M15, you should be able to tolerate 13 compression ratio, which gives you a 13% improvement. Offset against your 6% deficit, you have a net positive. Okay, now I don't, so I'm giving you the layman explanation. My previous speaker will probably give you the scientific one. But this is the layman explanation as to why methanol injection with a direct injected fuel is good for you. All right, now I'll go back to, and still, you will warn me anyway, so I'll do my best. So advance the thing. Yeah, here we go. So what I'm going to talk to you about is distributed production of fuels. And it makes sense for 2 situations, not for all situations. It makes sense if the raw material is highly distributed, and we'll give some examples, or if the let point, if you will, the US point, is highly distributed. Those are the only 2 situations in which it makes sense, and that you can almost let it cost more. All right, so distributed raw material. Some examples here. Shale gas is highly distributed. So each shale gas location will produce 50 to 100 times less than a location offshore. So you get smaller volumes from shale gas in general. Whenever you produce shale oil, you always get associated gas. In fact, with any oil except very heavy oils, you get associated gas. That gas is often in small quantities, because I told you, so the oil production also is relatively small from each pad, it's called. We ran some numbers, and the median number in the Bakken, which is one of the biggest producers of shale oil, is 50,000 standard cubic feet per day, which is almost nothing, okay? So on the open market, you'll probably get $125 for that per day. Try building a pipeline with that kind of revenue. So you don't. So they flare it. Okay? So that sort of accumulation begs for a solution. 50,000 is nothing. Okay? That gentleman said you can't make small units productive. Well, at 50,000 you can't do almost anything. So one of the previous examples was about a couple of million cubic feet per day was the example given earlier of producing gasoline. So these numbers are extraordinarily small, and they beg the question, can it be done? Biogas from water treatment is between 50 and 100,000 scuffs per day, standard cubic feet per day is the production. Again, almost nothing. So what do? They do what they can. If it's close to some place, they'll clean it up and put it in a pipeline. And if not, they flare it. God willing, they flare it. They don't let it go, but I think they flare it. In these applications, which is water treatment, as mentioned earlier, methanol itself is used for denatrification. Therefore, there's a nice closed loop situation. Take the gas, make it into methanol, use the methanol, and as it turns out, stoichiometrically, it actually works. About the methanol you need for denatrification is how much you would get from the gas. And then finally, biogas from animal waste impoundments, also known as swine lagoons. That is to not disturb our sensibilities. They're called lagoons. These guys, depending upon the size of the lagoon, somewhere between 100,000 and 1 million cubic feet per day. Still extraordinarily small from the standpoint of doing anything to it. The distributed fuel usage, I won't go into it. This has been mentioned before. The blending of gasoline, boats, DME for trucks. LPG blend, by the way, that was mentioned. I'll tell you that it's in many countries in the world it's being done. At 20% blend, the LPG doesn't even know you're there for any normal application. Also for diesel, you can put 20% DME into diesel and the engine doesn't know you're there. And it has benefits that were mentioned earlier. DME has no particulate matter, zero. Because it doesn't have a carbon-to-carbon bond, similar to methanol in that respect. And then there's hydrogen for automobiles, which we can argue whether it's going to happen, but it'll happen in California. So it'll be legislated to happen in California. Lots of stuff happens in California. So what is the need for, so basically, if you've got small volumes of gas, you can't economically move it on a pipeline. By the way, a conventional pipeline costs about $1.5 million per inch mile. That means a 5-inch pipeline is about $7.5 million. You see the problem. Small volumes cannot be transported by pipeline. But the gentleman in the back said, you can't do this. You can't do small units production economically. It challenges everything we learned in chemical engineering, everything. As sophomore chemical engineer, you said that you fail your exam, okay? Because it's something called economies of scale. And economies of scale really, really do work, okay? So the question is, can you challenge that orthodoxy? And the answer is a provisional yes. So you replace it with economies of mass production. That was mentioned earlier that one example they had was they built everything and brought it to location and just constructed on site. That's not how chemical plants are constructed, by the way. Each is custom designed. So this is, so these would be economies of scale on manufacturing, bring it in, assemble it, better catalysts, the chemical engineers call it process intensification. There's stuff going on. Whether it'll happen or not, we'll see. But another interesting point, the jobs are distributed. Okay, so these are not concentrated at the ports, which is right now. So for example, you take a little getaway from methanol, but 36 of the 39 ethylene crackers in the US are on the Gulf Coast. All there, okay? So you have to move the ethane down to there, and that doesn't happen. That's why ethane is dirt cheap, but that's a different story. And then here's an important point. It reduces pipeline infrastructure. If you can do it, see, people just build pipelines. Okay, they build transmission lines for electricity. There are other ways to handle this. So if you can do this, then pipeline infrastructure goes down. That's a good thing. Okay, pipeline infrastructure is not good for the environment. So I'm going to skip through this fairly quickly. This is a term I coined called just-in-place manufacturing, a little play on just-in-time manufacturing. But basically, we discussed this. We've got the mass manufacturing and scaling by numbers as being an offset to the normal economies of scale. The units can be short-lived. This is an important point. If you're building something and it's cheap to begin with, it doesn't have to last for 40 years. You can amortize it over 5 years. You can replace it in 5 years if it is cheap, and we'll come back to that. The small unit size, you can cluster them and make them a big unit clustered, or the small unit is distributed by itself, depends. Located close to the raw material, we'll discuss one example of that. And then the business risk is low because each of these units costs less, so it's easier to finance. Obsolescence risk is very low. You no longer have to amortize over 40 years. Therefore, obsolescence doesn't matter. When it's obsolete, you just replace it because it's cheap to begin with. So this is the concept, okay? How valid is all of this? So this is an example thing that's happening at RTI. I don't have any pride of ownership of this. I advise, and that's it. These days, that's all I seem to do. So what we have is flexible feedstock. It can be biogas, 5 minutes, okay, cool, can be handled. What it uses is a diesel engine. It's a regular diesel engine with some modification. It's spark ignited. Its timing is changed. So a diesel engine is inexpensive. So this is the chemical reactor. This chemical reactor is going to be less than $100,000 for 200,000 scuffs per day type of throughput. Well, in this case, it'll only 60,000 scuffs per day because this is a small engine. It's an 8-liter engine displacement. What this addresses is something that most chemical engineers don't address. So in this continuum of natural gas to gasoline, there's an intermediate step called syngas, synthesis gas, carbon monoxide and hydrogen. Most of the innovations happen on the back end of that. They take the syngas and do clever things to make it into gasoline or into methanol or into whatever. The first part has been relatively ill-addressed, and it's a high proportion of the overall cost. So that's what this addresses. This takes a simple diesel engine, modifies it, and produces syngas at a relatively low cost. You can do anything with syngas. The simplest thing to do with syngas, this is a non-partisan statement, the simplest molecule that you can produce from syngas is methanol. You can do other stuff, but methanol is the simplest molecule to produce. So if all you're trying to do is monetize this gas that is stuck somewhere, making the methanol is your best alternative. And I highlight only one other, which is hydrogen. And the reason I highlight that is for one simple reason. If you're going to have hydrogen cars, you need hydrogen filling stations, and you don't want to be transporting hydrogen over long distances. So production of hydrogen in a small location, a typical filling station is expected to require 300 kilograms of hydrogen per day. By the way, that's almost exactly what this little guy does. It produces 300 kilograms of hydrogen per day. So this is a general idea. And then let's talk about some Now, this is a very techie thing. We're going to skip it because we don't have time, but tech geeks can ask me about it. We will skip. Okay, here are the economics. The numbers from ADI, so that if you don't like him, complain to him, okay? All right? We just copied from them. So these are the numbers, and the ones on the right, the little yellow ones, is the range that we expect the engine and the reformer, I call it the micro reformer, the engine reformer to be. So you can see that, and this is pretty far along. I mean, this guy's been running for several months now. Or something like it. This is not the point. This is not it that's the point. Okay, the point is, can you produce syngas relatively inexpensively on a small scale, okay, for a net cost that is competitive with a large scale? That is a little mind-blowing, but it seems to be happening. I'm being very cautious because there's got to be, there's more work to be done. The more important point is let's challenge the industry to try and do this. Because if you can do this, it doesn't matter if that guy's doing it. If you can do this, it'll monetize small accumulations of gas, which otherwise you cannot do. Okay, and finally, this is really important. Horses for courses, it's a quaint British term indicating that certain horses run certain courses better. What it really means is one size does not fit all. So when you look at this, if you're on the vertical axis, it's gas quality. Quality is fewer impurities, higher C3, C4, higher valuable molecules. And then on the horizontal axis is gas field size. If you're on the upper right, lots of gas, high quality, you would build a full-scale 5,000 metric ton a day plant somewhere in the field, in Pennsylvania. That's going to happen, okay? When you're on the lower left, which is very small quantity, not very pure, not very high C2, C3, C4, higher molecules in the continuum, you'd go to this distributed guy, provided it was inexpensive. So that is the key point. These highly distributed, small production things are a part of the ecosystem. They don't replace anything. The last time I heard about silver bullets, it was the Lone Ranger. Thank you.
Wow, that was like a master class in methanol fuel blending altogether. That was great. We have time for a couple of questions. Shiva's got the microphone. Yep.
Okay, if you guys want to put your translator earpieces back on.
Thank you very much. I'm from Beijing, China. My first question goes to Door Chemicals. China has for M100, M85. However, we are still exploring M15. The biggest challenge is M15. After blended with gasoline, it will divide in different layers. So how do we overcome this issue? I'd like to know how your company deals with the challenge I just described in terms of M15. This is the first question. The second question is about energy security. The third experts talked about energy security. So right now, when we select energy, alternative energy, we have two principles. First is self-given, and the second is low carbon. That's why we use we use carbon-based methanol. However, we have a challenge with recycling of the CO2 in production. So I'd like to ask the third expert about what's your views on carbon-based methanol? Thank you very much. 第一个是讲的是
And the question was about how do you have a stable blend of M15 that doesn't have basically a phase separation? Are there co-solvents that you're using for an M15 blend?
It's a short answer. The answer is yes.
It's working.
Yeah, there are co-solvents which are used to make the blend stable. Like any fuel, it has a shelf life. Also, ordinary fuel has a shelf life.
Yes. And the second, yes.
It's about, I think it's about the carbon. I agree that most of the Chinese method of making methanol is carbon-based, certainly coal-based. I understand there's the energy security issue, so coal seems like a natural fit, if you will, for China. But as opposed to maybe getting into renewables for the production of methanol, we foresee, I think, more natural gas-based methanol production in China, like the rest of the world, which is obviously a lower carbon process. And in fact, I'm guessing here, but as China becomes more and more, as China comes more into its own in terms of its own natural gas development, which of course China, as some of you may know, has the largest shale gas resources in the world. As China starts to develop some of those resources, we think that natural gas should, in the long term, start to infiltrate in terms of becoming a lower carbon source of methanol.
So I have a response on the coal converted to methanol. Don't think of it like coal combustion for power. It is, the dirtiness is not equivalent. You first go to syngas, and then you can clean things up. And yes, you get more net CO2. That's true. Okay. But that's the only real thing. So the question, I think, was, the speaker recognized that there's higher net CO2, so what's to be done about that? What's to be done about that? I'm not going to give, the short answer is, the world should be looking at beneficial uses of CO2. We saw one example of that this morning, where you can electrolyze water to produce hydrogen, and with CO2 you can make methanol. So then why is it cost effective to electrolyze water? I'll give you a quick example. In Europe right now, when electricity is cheap, they're actually doing that, okay? They are electrolyzing water and producing hydrogen and making methane with it and putting it on the pipeline. That's subsidized because that's very costly. Methanol will be cheaper than making methane, much cheaper. So if there are situations where you've got waste electricity, if you will, or whatever, if there are certain situations, you could electrolyze water, make hydrogen, and then react it with the CO2. So, but I think we, in general, all of us should be looking at CO2 utilization. Beneficial, not putting it in the ground.
Yep, we've got another question in the back.
Thank you. Sarah Jordan, I'm a faculty member at Johns Hopkins University. First, I'd like to say it was a really wonderful panel. My question is specifically for Geely Group. I thought that the presentation was really wonderful illustration of the advancement of innovation. I'm interested in how you see the market evolving not only in China but globally, and if your company has plans to evolve in that direction.
这个你的比较噪音比较大，没听清楚。那问题再给我陈述一下。
The question was about, does Geely have any plans to introduce a methanol product globally?
Right? Did you want to ask it? Okay.
就是吉利的刚。
So in this question, I'd like to. So I think Geely is not very determined on this issue. 那么这个
是不是可以再讲的再准确一点？
Could you please clarify your question, please? 那么我来
Methanol can be made from coal for under about $250 a metric ton, US dollars a metric ton. That's because of their vast experience and the fact they've done that. I fully expect India to follow suit. Now, there'll be policy implications and so forth, but they have got a lot of coal. India's got the third largest coal deposits and so forth, So if they go to methanol, they will get it from coal, and they will be able to use Chinese experience to do it.
Maybe we can ask that question separately to Mr. Jen. So I want to thank the panelists for joining us. We do have gifts for each of our speakers. And before we have our lunch, which again will be served right here, in the interest of time, we'll have to move on, sorry. Before we break for lunch, and actually the lunch is going to be served right here, so you don't have to get up, we have a very special award to present. So George Olah was a pioneer, visionary, and Nobel Prize-winning chemist. It was with great sadness that we received news in March that he had passed away. His book, Beyond Oil and Gas, The Methanol Economy, is a seminal work which provides a clear path forward for humanity to transition to using methanol as a transportation fuel, energy storage medium, and raw material to replace oil. Today we will present the first George A. Olah Memorial Lifetime Achievement Award to a very deserving recipient. Here to present this award, I'm honored to have my good friend Surya Prakash, who co-authored Beyond Oil and Gas, The Methanol Economy with Dr. Olah, and worked closely with him at the University of Southern California for many years. Surya is the George A. Olah and Judith A. Olah Nobel Laureate Chair in Hydrochemistry at the local Hydrocarbon Research Institute at the University of Southern California. Like George Olah, Surya is the leading authority on the field of hydrocarbon chemistry and the creation of the methanol economy. In fact, he quite literally wrote the book on the methanol economy. It's my great honor to welcome Professor Prakash to present the George A. Olah Memorial Lifetime Achievement Award.
Good morning, ladies and gentlemen. I'm delighted and I'm honored to present the George Olah Memorial Lifetime Achievement Award to Paul Wuebben. Is Paul here? You can come and stand here for a minute and I can tell what you have done. Paul Wuebben has done many things in his career. In fact, we call him in California Mr. Methanol. In fact, he was instrumental in introducing methanol as a drop-in fuel in the late 80s. In fact, Los Angeles County experimented with 10,000 vehicles running with M85 over a several-year period. And Paul Wuebben has been an EPA fellow at the Harvard University, and he also was the founding member of the Methanol Task Force of California Energy Commission, California Air Resources Board, and Southern California Air Quality Management District. In fact, he was the Clean Fuels Officer between 1990 and 2011 at Southern California Air Quality Management District. He has been a clean fuel advisor to the chairman of the California Air Resources Board. And right now, he's working as a senior director of renewable fuels at the Carbon Recycling International, the first company which makes renewable fuel using geothermal electricity, carbon dioxide, and water. In fact, that plant is named after George Olah. It's called the George Olah Renewable Methanol Plant. With that introduction, I am delighted and happy to present on behalf of the Methanol Institute the inaugural George Olah Memorial Lifetime Achievement Award to Paul Wuebben. Congratulations.
goodness, this is heavy, kind of spectacular. Thank you, Dr. Prakash. And first, to thank you and your colleagues at the Locher Institute. It's really a great, profound honor, really, for me. I was very fortunate to know Dr. George Olah personally, and I found his vision and leadership really inspired me for many, many years. Receiving this award is something I honestly never expected. I first want to thank my wife, Elena, who's, I'm lucky if she's here, and our family for their love and their support over the many decades. My success professionally really wouldn't be possible without their great encouragement and understanding. And I can imagine my mother, my father, my brother also looking down right now and asking, how in the world did this happen? And that's a good question. I'd have to say that the candid answer is that I stand on many, many broad shoulders. People like Roberta Nichols of Ford Motor Company, the woman who created the flexible fuel vehicle, the former chairman of the California Energy Commission, Chuck Embrecht, the founder of Carbon Recycling International, K.C. Tran, our CEO at CRI, Mr. Sinderson, V. John White of the Center for Energy Efficiency and Renewable Technologies, Mike Jackson at the Fuel Freedom Foundation, and I'm pleased that my friend Ken Smith from the California Energy Commission and their methanol program is here today as well. I also want to thank Greg Dolan and Gal Luft for their great leadership on this issue. I would like to say just briefly that when I began my career as an EPA fellow at the School of Public Health at Harvard, I was struck by the deep personal commitment that virtually everyone there in the health sciences had to improving public health and welfare. And I was very fortunate in my career, and I continue to be given numerous roles to essentially integrate my understanding of urban air pollution with a growing understanding of energy and transportation fuels. I've had the opportunity to be at the cutting edge of fuels and vehicles research and development, and also at the cutting edge of major policy formulations, both in California and in front of people like John Dingell for his masterful way that he would hold his hearings. And as one of the founding members of the California Methanol Task Force, I think that we were privileged to see the creation of some really key technologies. I consider the most important success out of that methanol program was the creation of the flexible fuel vehicle. And remember that I believe it's no exaggeration to say that that single innovation was the cause for the Brazilian miracle. That innovation allowed the 100% penetration of vehicles into a marketplace, Brazil, that are not dependent on fossil gasoline. I've also had the good fortune to be present at the creation of many alternative fuels and technologies that we take for granted today. The first methanol bus, the first compressed natural gas bus, the first liquefied natural gas bus, the first fuel cell bus, the first plug-in hybrid, the first EV1, which named the Impact. And more recently, several years ago, and since I've joined CRI, I've had a great honor really to participate in the design, commissioning, and operation of the world's first, what I call the CO2 refinery, industrial scale CO2 refinery. We've proudly named that the George Olah Renewable Methanol Plant. And just imagine the significance of that plant. We do not use any fossil fuels. It converts carbon dioxide, captures carbon dioxide, uses renewable electricity, and produces renewable fuel. The last thing I'd like to say, then, distilling the lessons really that I find in my career, the one thing that I would distill of policy significance is that we're just one policy away really from energizing significant economic development and public health. And that, namely, is essentially the replacement of the renewable fuel standard with an open fuel standard. Just think, we do not burden our innovations in telecommunications by requiring that the iPhone software of today be compatible with a rotary telephone of the 1980s. In contrast, where we require existing fuels to be compatible with the cars of yesterday, rather than requiring the new cars to be compatible with the fuels of tomorrow. So on behalf of my family and, of course, my colleagues at Carbon Recycling International, I'm very proud to accept this award. And like George Olah, who redoubled his efforts after he received his Nobel Prize, I'm committed to try to do the best that I can to continue to work in this area to really show my commitment and the distinction of this honor. So thank you very, very much.
Thank you.
Again, we're going to be serving lunch right here in this room. This is a good time to get up, stretch your legs a little bit while they bring in the plates and the silverware, and then we'll reconvene shortly with the distinguished members of the U.S. Energy Security Council.